Right. So I just name this integrator block based on what it does. And this integrator block integrates angular acceleration into angular velocity. So I'll name it appropriately as well. Angular acceleration to angular velocity. So it's just a nice practice to name these blocks appropriately. And that's not it for step one. If you double click these blocks, you'll see that an dialog block pops up where you have to specify certain conditions before you proceed to step two. At the moment, ignore all these conditions other than the initial condition. What we'll be discussing in this lecture today is only initial conditions. You can figure out what other conditions mean by checking out the documentation. Now, the initial condition is where we specify our initial values. Now, remember in MATLAB, we declared a variable to hold the initial values for angle and angular velocity. And these initial values were determined based on the observation that we made. If I recall them, the observation that we need to make are the simulation starts at the start of the simulation, the rod is at rest, and the rod is at rest at an angle 30 degrees to the horizon. So now based on these two observations, we'll specify the initial conditions of these two integrator blocks. Now if we take an integrator block, the initial condition should be the initial condition of the output of the integrator block, right? So if I take the integrator block angular velocity to angle, the output of this should be angle theta, and in the initial condition box I should specify the initial condition of the angle. So from our observation we have that the initial angle is theta degrees. So we work in radians, and we have to convert it into radians prior to inputting it in the box. So I have done the unit conversion, and the 30 degrees is 0.5236. Right. So that's done. And for this integrator block, the initial condition should be the initial condition of the output of it, that is the initial condition of angular velocity. From our observation, the rod starts at rest, which means the angular velocity is 0. So 0 is same whether it's in RPM, radians per second, or any other unit for angular velocity. So I'll just leave it at 0. So that's it for step 1, and then we'll move on to the next step. So now step 2 requires us to bring in constant blocks as required by the ODE. Now to figure out what the constants we need to bring in, now we need to take another look at the equation we developed. So we have constants I, A, M, G, L, and B. Uh, 6 constants. But I can be expressed as an equation of M and L. So as in addition to what we did in MATLAB, we'll be expressing I as an equation of M and L in the Simulink model as well. Since we do that, we will be using only 5 constants A, M, G, L, and B. So I will bring them in, give them the appropriate values, and name them. So I know the block that I'll be using is a constant block. Double click and type in the name. Sorry. Yeah. I need one for M, G, L, A, and B. So let's name this M. So M is mass, which SI unit for mass is kilograms. So we'll run the study for a mass of 0.5 kilograms. If you want to change the study for another case later on, and all you have to do is come back, double click on this block and change the value. And the value will be displayed in the block as well. G is 10 meters per second in SI units. L is another system parameter that we can change. For this case, we'll keep it at 200 millimeters, which is 0.2 meters in SI units. A and B are the values we obtained after modeling the torque versus RPM, or the torque versus angular velocity relationship for permanent magnet DC motor in a y equals ax plus b form. So these are the constants, and I will bring them in as well. Right. So we have specified 5 constants, and the 6th constant I can be expressed as a function of m and l. Now we can use some math operation blocks available in Simulink to build up L. So the equation that we have for L is 1/3 times m times L squared. We can obtain a square block to obtain the square of L, multiply with it m, and use a gain block of 1/3 to obtain I. But however, I'll be using something called the MATLAB function block, where I'll just use one block and implement that equation. So I double click the function block, and it gave it opened up the MATLAB script editor. You start by specifying the end keyword. This is not the statement that we want, so I erase it. So we'll have one output. I'll appropriately name it I. I'll rename the function to calc I, and the inputs would be mass and m. I'll specify them as mass and length, and we need to specify the statement which expresses I in terms of mass and length. So I would be 1/3 times m times L squared. So that's it. Save that function and come back to the canvas, and you connect mass and length blocks into the respective inputs of the function block, and then you can obtain a signal for I from the output. So now, why did I use this block instead of using Simulink operations? For even more complex expressions than the one we implemented right now, relying on Simulink blocks would result in a heavily in a large combination of blocks, which would obscure the main model that we are implementing. So using the MATLAB function block is quite